Have you ever looked at a complex electronic device, like your phone, and just wondered, how does it all work? Well, a huge piece of that puzzle is a surprisingly simple rule called Kirchhoff's voltage law, or KVL for short. It's one of the keys to understanding almost any electrical circuit, and today we're going to break it down.
But before we even think about circuits, let's start with something way more familiar. Imagine you go for a hike on a trail that loops all the way back to your car. You go up some hills, down into some valleys, but when you get back to the exact spot you started, what's your total change in elevation? It's zero, right? You're right back where you began. Now, hang on to that idea, because it's pretty much everything you need to know.
So, here's the really cool part. That simple idea from your hike, it perfectly explains how electricity works in a circuit. That change in height you experienced? Well, in electronics, that's what we call voltage. Let's see how that connection works. And there it is. Just like your total up and down hiking came out to zero, the total change in voltage around a closed circuit loop is also zero. See, the electrons in the circuit get a boost of energy from something like a battery, and then they lose that exact same amount of energy as they go through all the components. They end up right back where they started, electrically speaking. Now, this whole idea has a formal, official-sounding name, Kirchhoff's voltage law. The textbook definition says the algebraic sum of all voltages around any closed loop is equal to zero. I know, that sounds a little dense and academic, but don't worry, the idea behind it is way, way simpler. Let's just cut through the jargon. Here's what that definition really means. In any circuit loop, the amount of energy that gets put in, we call that a voltage rise, has to be completely used up by all the parts in the circuit, and we call that a voltage drop. The rises have to perfectly equal the drops. What goes up must come down. It's a perfect law of balance.
You might be asking, okay, but why? Why does it have to be that way? Well, it's not just some random rule for electronics. It's tied to one of the most fundamental laws in all of physics, the conservation of energy. You just can't create energy out of thin air, and you can't make it vanish. The energy that a battery provides has to go somewhere, and it gets used by every single component in that loop. There's nothing left over.
All right, that's enough theory for now. Let's actually see this law in action. We're going to look at a really simple circuit and walk through it step by step to see exactly how KVL works in the real world. So every circuit needs a power source. In this case, it's a battery. This is our uphill climb in the hike. It provides what we call a voltage rise of 10 volts. Think of this as our total energy budget for the whole trip around the loop. We've got 10 volts to spend. Okay, so the current starts its journey and immediately hits our first component, a resistor. Resistors, well, they resist the flow, and that takes energy. This one uses up 3 volts of our energy, so we call that a voltage drop of 3 volts. We've already spent 3 of our 10 volts. Next up, the current flows through the second resistor in the loop. This component uses up all the rest of the energy, causing one final voltage drop of 7 volts. So, we started with 10, we dropped 3, and now we've dropped another 7. Let's see if the math works out.
And look at that, it's perfect. The battery gave us a rise of 10 volts, the first resistor dropped 3, the second dropped 7. You add those drops together, 3 plus 7 is 10. The total rise equals the total drop. Every single bit of energy that was supplied got used. No more, no less.
This is how we write that down using the formal KVL equation. We think of the energy gain from the battery, the rise, as a positive number. And we think of the energy losses in the resistors, the drops, as negative numbers. So you have a positive 10, minus 3, minus 7. And what does that equal? Exactly 0. The algebraic sum is 0, just like the law says it should be. Okay, that makes sense for a simple example. But how do you actually use KVL to figure out a circuit where you don't know all the values? Well, it turns out there's a simple 5-step process that works every single time. Think of this as your new toolkit for circuit analysis. So here they are, the 5 steps to KVL glory. First, you just pick a closed loop in your circuit. Second, you pick a direction to travel around it. Clockwise, counterclockwise, it seriously doesn't matter. Just pick one. Third, as you trace that path, you label all your voltage rises and drops. Fourth, you write out the KVL equation based on your path. And finally, step 5, you just do the algebra to solve for whatever you're looking for. It's a foolproof method.
Now, you might be thinking, okay, cool, it's a neat little rule for a classroom problem. But why does this really truly matter? Because this isn't just theory.
This is one of the most powerful tools that engineers use every single day to design and build the world around us. I mean, we are talking about everything from the massive power grids that light our cities to the tiny little circuits inside your smartphone. Engineers are constantly using KVL. It lets them analyze incredibly complex networks, design brand new electronics, and make sure everything works the way it's supposed to. It is truly a cornerstone of all electrical engineering. So if you only remember one thing today, please let it be this. A circuit is just like that hiking trail. In any closed loop, what goes up must come down. The total voltage rise will always equal the total voltage drop. It's the law of balance. You know, Kirchhoff's voltage law, along with its partner Kirchhoff's current law, really are the foundation for everything else in circuit analysis. Once you've got a good handle on these two principles, you basically have the keys to unlock and understand almost any circuit out there. The only question left is, what are you going to analyze first?